Hello and welcome to this next round of videos in Mathematics 2. Today we're going to start approaching the question of optimization algorithmically. So what we have seen so far is analytic ways of computing possible candidates for local minima or maxima. But of course, in practice, the functions that you deal with are often so complicated that you cannot really approach this question analytically. Let's say if you have a function that is defined as a solution of a complex differential equation, then it might be even more complicated to get a hold of first and second derivatives so that you can actually solve these, find their roots, and then characterize them. So what is more important in practice is an algorithmic approach to these questions. And that's what we're going to get a quick glimpse of in these next few videos. So our topic is algorithmic approximation of local optima. That's 14.3. Algorithmic approximation of local optima. And as you can see from the title already, our aim is not to compute the precise local optimum. Our aim is to compute points that are close. So we just want to approximate, and that's the best we can hope for in realistic, real-world situations. First thing we'd have to do here is we'd have to get an idea of what the gradient actually means geometrically. So that is going to be our first topic for today. We're going to look at the interpretation of the gradient. Okay, so let's say we have a function f. So we consider the function f on some open set x into the real numbers, and let's say that function is differentiable at some point x star in x. Now if we select a certain direction, then we can restrict f to that direction, and we can have a look at the behavior of f along that direction. And in particular, the directional derivative of f in a certain direction will give us the derivative in that direction. So it will give us an idea of the change rate of f as we're walking along the line in direction v. Okay. So for a direction v, that's just any vector in Rn with the exception of the zero vector. And let's say we normalize v, so the norm of the direction should be 1, meaning the length of a direction will not influence the directional derivative. Okay, so we normalize to 1. And then we look at the directional derivative. So that's dvf at x star. And what that represents is the local rate of change of f at this point x star in direction v. So if we're moving in direction v out of this point x star, then that is the rate with which the function value changes. If it's high, then we'll expect a high rate of change in the function value. If it's low, the function value will rarely change. Okay, so this is the local rate of change of f at x star in direction v. And what we want, of course, if we want to optimize a function, then we'd like to find the direction that has maximum rate of change, either in the positive or in the negative sense. So we'd either like to have a maximum positive rate of change and walk in that direction to increase the function value as fast as possible if you want to maximize. Or if you want to minimize, then we'd like to find the minimum rate of change, meaning a negative rate of change if possible. And we'd like to walk in that direction to get the function values lower as quickly as possible. So the question is now, how does it all compare to the gradient? We know that the directional derivative is related to the gradient. In particular, we know that dvf at x star is the same thing as the gradient of f at x star transposed times v, or in other words, the scalar product of that gradient and the vector v. Now, what do we know about scalar products? There's one thing in particular that we know, that we have made use of in the past, and that is Cauchy-Schwarz inequality. So we know that this scalar product here is less or equal to the product of the norms of the two factors. So this is less or equal to the norm of the gradient times the norm of v. And that is due to the Cauchy-Schwarz inequality. Okay, so, well, we normalized v, remember? So this is actually equal to the norm of the gradient. Okay, so what that means is this rate of change is actually bounded by the norm of the gradient. And remember, Cauchy-Schwarz's inequality also holds if we add absolute values. So this is still true with absolute values, and that also means it's a lower bound as well. Yeah, it also bounds the negative value of the directional derivative from below. Okay, so what that means is the norm of the gradient, this value here, is an upper bound, and the negative norm of the gradient is a lower bound. So plus minus that norm is a bound on the rate of change. Okay, so the function cannot change faster than what the gradient says. On the other hand, if we choose the gradient itself as the direction, then, well, what do we get then? Let's see. If we set v equal to the gradient, and then of course we have to normalize, divide by the norm of the gradient as well. So if you set v like this, what do we get? Well, what we obtain is dv of f at x star for that particular direction. Well, that is then precisely the gradient transposed times v, and v is the gradient, divided by the norm of the gradient. And you will remember that a vector transposed times itself, so gradient of f times gradient of f, that's exactly the norm squared of a vector. Okay, so what we have here is, in fact, the norm squared of the gradient of f at x star divided by the norm of the gradient of f at x star. So that will cancel out. And what is left is just the norm of the gradient. So what does that mean? Well, if we choose v as a direction, then we actually assume that bound. So that's the maximum rate of change that we could get. And of course, we can realize the minimum rate of change by just choosing the negative gradient. Okay? So let's make a quick note about that thought, because that's the main take-home message for today. The gradient is the direction of maximum local change. That's basically the message of the gradient. So the gradient nabla f of x star is the direction of maximum local increase of f at the point x star. And of course, we can also turn this around and take the negative gradient, and then we have maximum local decrease. So likewise, minus the gradient of f at x star is the direction of maximum local decrease of f at the point x star. Okay, so that's basically what the gradient tells us. In which direction in the domain do we have to move to increase or decrease the function value as fast as possible? Now let's just define a quick name for that fact, because we're going to use that in our algorithms, of course. So if we have a function, then these directions, normalized directions, are called the directions of steepest ascent or steepest descent at a point x star. Okay, so as usual, let x be a subset of r to the n, open. Let f be in C1 on x, so continuously differentiable on x, x star a point in x. And of course, we also assume that the gradient is not 0 at x star. Otherwise, we cannot divide by the norm of the gradient, because that would then be 0 as well. Okay, and then we define those two directions. And those are the gradient of f at x star divided by its norm, and the negative of that direction, so minus the gradient divided by its norm. Now these two are called direction of steepest ascent or descent at x star, respectively. Okay, finally, let's have a look at the geometry. So the gradient is a vector that lives in the domain. That means it's particularly enlightening to have a look at the domain of a function and then see how the function behaves there. So what we will often look at in this context is the level sets of a function, the contour plots. So just to sketch you a quick example, let's say we have a function on R2. So this is the x1, x2 plane. And let's say that function that will have contour lines that look something like this. So say we have something like a parabola, right? Maybe not quite a parabola, so it's not quite circles. Okay, so let's say this is the level sets of a function. And we want to know about the gradient at a certain point x star. Say we choose this here as our point x star. Now, what is the direction of steepest ascent and descent in that direction, and therefore the gradient? Well, if we're moving along the level set, then nothing changes. Yeah, ascent and descent will be 0. That means if we would be moving along a tangent to the level set, something like this here, again, not much would change. So as we're close to x star, we are close to that level set of the same level, and that means the change is very, very slow. So what we want to do for maximum local change is move away from that level set in an orthogonal direction. And that's precisely what the gradient is doing. So this is the tangent, then the gradient would be this. Okay, so this is orthogonal to that tangent. That would be the gradient of f at x star. That's the direction where we have the steepest local ascent. And of course, the negative gradient then looks like this. Yeah, so that's minus df of x star. Okay, so the direction of the gradient is orthogonal to the level set through any given point. The direction of plus minus the gradient f at x star is orthogonal to a tangent at the level set of f through x star. So that means if we have contour lines, then it's easy to find the direction of the gradient for a given point on those contour lines. Okay, so that's the geometry of the gradient. That's the algorithmic meaning as well. We now know where the local steepest ascent and descent is, and that means algorithmically it might be a nice idea to just follow that. So if you want to minimize, we just start somewhere. We follow the negative gradient to get a decrease in the function value, the steepest possible decrease in function value. We just do that for a while and then we reevaluate. And that's exactly the first algorithmic method that we are going to present in one of the next videos. I'll see you then.